Good afternoon, BS Computer Science students. I'm Professor Froilan de Guzman, and I'm about to discuss the AVL Trees, which is one of the branch topics under the tree data structure for data structures and algorithm course. Okay, so before we start with our discussion, uh, let us expect at the end of this PowerPoint presentation, we are able to calculate the balance factor of each nodes on the binary tree. We are able to use the different rotation types. These are the following methods for us to do the balancing on the binary search tree. And of course, as part of the major procedure in AVL trees is how to perform self-balancing. Okay, let's proceed. What is AVL tree? Actually, AVL tree is a self-balancing binary search tree. We all know that for every nodes or every items that you're about to enter or about to insert on your tree data structure, there is a possibility that your binary tree will become complicated in terms of searching. So just for example, if you have different um, entries on your binary tree, there is a possibility that uh, your binary tree will become skewed, left skewed, or rightly skewed. So this will compromise the searching functionality of your binary tree. For example, if I have a tree data structure that composed of 1, 2, 3, 4, so if I'm about to search data item 4, it will search into different nodes before you reach the desired item or desired data item that you're about to fetch on your data structure. The main purpose of AVL tree is to perform self-balancing. When we see self-balancing, you are trying to make your binary tree in a perfect concept, meaning to say that these data items are more searchable, which is uh, which is promotes us to have a limited number of edges from the root. Remember that when you're about to search any data item on a binary search tree, it is always start with the root node. Now, you are attaching different data items that will arrange where in fact you are minimizing the number of edges or you are minimizing the depth of the tree. Okay, so that is one of the advantages or reasons why we are performing AVL3. All data structures that you are that using a binary search tree definitely use an AVL3 for us to minimize or simplify the binary search tree in order to promote more accurate and efficient data searching on your binary tree. Now, in performing balancing in AVL3, it is a must that you must know how to compute for the balance factor. So what is the balance factor of a node? Take note that for a given binary search tree, you're about to compute all nodes, the balance factor of all nodes. And for making the entire binary tree qualified as a balanced binary tree, so it should have a balance factor ranging only from +1 to -1. So any other values which is about to occur or emerge on your balance factor more than +1 or less than -1 is considered unbalanced. That's why you need to perform different rotation. By the way, in this particular um, reference that I have here, the balance factor is just being computed using the difference between the height of the left subtree and then the height of the right subtree. Okay, so so the self-balancing property of an AVL tree is maintained by its balance factor. As I mentioned, it should be ranging only between -1, 0, and then +1. Okay, what if that your nodes, one of your nodes inside your AVL tree has a balance factor more than 2 or more than 1 or less than -1. So the smallest value rather is +2 or -2. Okay. So just for example, I have this kind of sub tree. I have a nodes A, B, and then C. So how can I compute for the balance factor? So for example, let's go back from our previous slide. We have 0 here because this particular node has no children. So meaning to say the left subtree, the height of the left subtree minus the height of right subtree is 0 minus 0. So the balance factor is 0. Okay, so for node 21, so you have 1 left subtree minus no right child, so that is 0. So 1 minus 0, you will have a balance factor of 1. Okay, so for this particular node, node 9, so you have a height. Take note, a height is being computed by counting the number of edges until you reach the leaf node. Okay, so we have 1, 1, 1, which is 2. So that is 1 minus 2, and then you will get -1. And then for the root node, which is 33, so the height of the left subtree is 3, and then the right subtree is 2. So 3 minus 2, and you will have a balance factor of 1. Okay. So far, by this particular example, there is no nodes uh, that reaches +2 or -2. So meaning to say this that this entire binary tree is balanced so far. So let's proceed with the next slide. So just for example, I have here A, B, C. So take note that the balance factor for node C is 0. Okay, so this one is actually 0 minus 1. So this should be -1. For this particular reference that I have, it simply denoted that the right sub 3 minus left sub 3 is the computation for its balance factor. So actually, regardless of positive or negative, for as long as that the difference of the left and right sub 3 to each other will become more than +1 or -1. So uh, given the it is obviously that the one of the nodes of your given AVL tree has a balance factor of 2. So you need to perform a certain um, procedure for you to make the entire tree balance. So just for example, in this particular sub-tree, so I have A, B, C. So the balance factor of left node, the leaf node C is 0 because this particular node doesn't have any children. So that is 0 minus 0. So this one, the left child tree has no children. So that is 0 minus 1 or simply -1 or as I mentioned, -1 or +1. So obviously for node A, so the left child is not present. So that is 0 minus 2. So you will have a balance factor of -2 or +2. Now, if you have a uh, rightly skewed rightly skewed part of your subtree, so you need to perform a left rotation. So when we say left rotation, So the middle node, that will become a new root node. So just for example, that is node B. You will rotate it counterclockwise, and now node B will become a root node. And what will happen? So your A, which is previously the root node, will now become a left child for node B, and then node C is still the right child for node B. So this will be the balance subtree for this particular subtree. Okay, the previous subtree that we have here will now become balanced. If you will try to recompute the balance factor of each node, so each of the nodes will now become zero. The balance factor will now become zero. Okay, so for the right rotation, so the example is quite symmetrical with the previous one. So the difference is the concentrated height of the children is on the left side. Okay, so you will perform the right rotation. Okay, so for this particular given, the node B will now become the root node. So you will rotate the nodes on a clockwise format. So obviously, B will now become the root node. A is still the left child of node B, and C will now become the right child of node B. And if you will try to recompute the balance factor, obviously each of these will become zero. Okay? So the qualification for AVL tree, take note, is all of the nodes should be positive 1, negative 1, or 0. So we have the left-right rotation. So obviously, so we have CAB. So when we say left-right rotation, left-right, so you will perform first the right rotation and then the left rotation, or rather left rotation and then right. Okay, so obviously when you have this kind of structure, so the root or the node B will become your new root node. Okay, and then node C will eventually become the right child of node B, and then the node A will become the left child of the root node B. Okay, so for every instance that you will encounter this kind of unbalanced subtree, so take note that the leaf node will become a new root node. Okay, so left right. Okay, left right rotation. Okay, so you will perform left rotation and then right rotation. That will make your node B as the new root node. Okay, so we have the right left rotation. So obviously right and then left. So upon performing the right left rotation, so you need to perform first right rotation and then left rotation. And eventually, your leaf node B will now become the new root node. And then A will become the left child of node B. And then the right child, or the node C, will become the right child of new node B. Okay. So this is the basic structure. Okay. Now, upon doing this, obviously your AVL tree will now become balanced. Okay, for us to appreciate the nature of AVL tree, so let's have a particular example. So let us assume that these following inputs are entered on the AVL tree with this sequence. So 15, 7, 28, 5, 3, 10, 30, 33, 6, 21, and 20. Okay. So let us now enter 15. Okay. So when I entered 15, so obviously there's no left child or right child. So the balance factor is 0. Now I entered 7. So we all know that the new data item is less than the root node. So obviously it will um, set as the left child of the root node. So the balance factor for node 7 is obviously 0, and then the balance factor for 15 is 1. Okay, we have 1 minus 0. Okay, now let's proceed upon entering 28. Okay, so obviously the entire binary tree is still balanced. Okay, so now let us enter 5. Okay, so when I enter 5, so obviously a leaf node has a balance factor of 0. Node 7 has a balance factor of 1 minus 0 because it doesn't have a right child. Node 28 has no children, so obviously it has a balance factor of 0. The root node 15 has two edges or height on the left subtree and then 1 on the right subtree. So 2 minus 1 is 1. So obviously, the entire binary tree is still balanced. Now, I entered 3. Okay? So when I entered 3, so it is less than 15, less than 7, less than 5. So 3 will be inserted on this location. So now, obviously, when I try to compute for the balance factor for each node on this AVL tree, you will notice that you have two nodes that has 2 or balance factor of 2. Now, when will you perform rotation or the right rotation? So are you perform the right rotation or right rotation on this part or on this part? Okay, so obviously when you're about to perform the right rotation, you just simply perform on the leaf node or the leaf node side. Okay, because obviously when you perform a right rotation on this part will automatically arrange the balance factor and it will adjust any parent node on this particular subtree. It will also adjust. The balance factor will also adjust. So when I perform a rotation on this part, obviously 5 will now become the root node. And then you will perform the right rotation. Okay. So now obviously this will now uh, this will now the updated AVL or binary search tree. Okay. So node 5 is now the root node for this particular subtree. Okay, so obviously the entire tree is now balanced, and now let us try to enter data item 10. Okay, obviously, what happened? Okay, obviously, we have a balance factor which is equals to 2. Okay, so in what location do we need to perform a rotation? Okay, so obviously at this part. Okay, okay. In a location where when there is a node that violates the balance factor, which is more than 1 or less than -1. Okay, so this is obviously a left-right rotation. So you need to perform left-right rotation. Okay, now take note, 7 will become the new root node. Okay, 5 will become the left child, and then 15 will become the right child. of the new root node. Okay, so what happened on node 10? So obviously node 10 will hang, okay, but upon entering node 10, it is greater than 7. So you need to put it on the right child of node 7. And it is less than 15. So you will put it on the left child of node 15. Okay. Now, let us enter 33. So still, the entire binary search tree is balanced. When I entered 6, okay. When I enter 21, okay. What if I enter 20? There is a part of our binary search tree that we need to adjust. Okay, so we need to perform the right left rotation. Okay, so obviously node 21 will now become a root node. Okay, and then that's it. Okay, so this is the entire ABL tree, ABL tree, or the balance tree or binary tree upon entering this following data item in sequence. I hope you learned something from me today. Okay, and then uh, you may ask questions if you have some clarification or inquiries about this topic. Thank you very much.